Validity. In everyday language, a person utters a validity if he or she says something which is true, but only because of its form. Like, quote, every day is rainy, or else some days are not rainy. A formula of predicate logic is valid, or a validity, if it is satisfied by every assignment in every structure. Here are some examples. Exists xa if and only if negation for all x negation a. This is obviously valid. It can be proved valid in many ways, but for example, one can take a structure and an assignment such that they satisfy exist xa and then make the conclusion that it's not possible that every x satisfies not a in that model, because there is one x which satisfies a. And conversely, one takes a model and an assignment which satisfies negation for all x negation a, and then concludes that there must be an x which satisfies a, because otherwise every x would satisfy not a, and that was not the case. Next example, for all x a, if and only if negation exists x negation a. Here one can argue just as in the previous formula. Then exists x left parenthesis a or b right parenthesis if and only if left parenthesis exists a disjunction exists x b right parenthesis. One could say that existential quantifier commutes with disjunction. So this is proved to be valid by taking a model and an assignment which satisfy that exists x, a or b. Then this x which satisfies a or b satisfies a or b. And according to which one it is, we get that this assignment satisfies there exists xa, or it satisfies there exists xb. And in the other direction, if the assignment satisfies there exists xa or exists xb, then whichever it is, we have an element which satisfies a or b, so the left-hand side of the equivalence is also true. In the same way, one can prove that the next formula is a validity for all x a and b, if and only for all x a and for all x b. We would say here that the universal quantifier and conjunction commute. Finally, for all x equal to x. Now this is a validity because whenever we have a formula with the identity symbol, we assume the identity axioms. So if we take an assignment and a model and we assume that they satisfy the identity axioms, then they satisfy this for all x equal to x, because this is one of the identity axioms. Satisfiable. A formula is satisfiable if it is satisfied by some assignment in some structure. A statement of everyday conversation would be considered satisfiable or plausible if things could be like the statement says, and maybe even are. If I say, quote, there is intelligent life outside the Earth in our galaxy, unquote, this would probably be considered plausible, possibly a true statement, although we really do not know. And there is a chance that I am wrong. This is what satisfiable means. But now we are talking about predicate logic, so satisfiability has a technical meaning, namely being satisfied by some assignment in some model. For example, for all x there exists y r0 xy and negation exists y for all x r0 xy. Now this is satisfiable because we can think of a model with interpretation of r0, so that in this model for every x there is a y such that r0 xy, but we don't have any y so that for all x r0 xy. By just thinking a little bit familiar examples, it's obvious how to construct such a model. A second example, for all x p0x or p1x, and left parenthesis negation for all x p0x or negation for all x p1x, right parenthesis. This is a conjunction, and the first conjunct says p0 and p1 cover all cases, they cover entire universe. The second conjunct is a disjunction, which says that either p0 is not everything or p1 is not everything. When one thinks about this for a moment, it's clear how to find such a model. So this is satisfiable. Finally, negation left parenthesis exists x p0x implies for all x p0x. So this is a negation of the rather crazy claim that if there is something in p0, then everything is in p0. So one just has to find a model with a p0 so that p0 has something but not everything. A formula is contingent if it is both consistent and refutable. A person utters a contingency like, quote, it is raining, unquote, quote, someone is vacuuming upstairs, unquote, or, quote, Bach is the greatest composer of all, unquote. If what he or she says can be true but can also be false, so contingencies are satisfiable, but not conversely, as validities are examples of satisfiable formulas which are not refutable. Here are some examples from predicate logic. For all x p0x, so this says that the interpretation of p0 covers the entire universe. Of course, this is contingent. In some models it does, in some others it doesn't. Then, exists x for all y r0xy. Again, who knows about R0? In one model this is true, in another it is false. For example, R0 could be empty, then this would be false. R0 could be the entire Cartesian product of the universe with itself, this would be true. Next example. There exists x left parenthesis R0xy and p0x right parenthesis. Note that here is a free variable y. Such formulas are rarely contingent because they probably depend on the interpretation of y. And indeed, it's the same here. It's easy to think of examples where an assignment for y satisfies this and others where it's not satisfied. Finally, x equals y. So this is a formula which has identity, so we are only considering models of identity axioms. But still, our assignment might assign the same value to x and y, then this would be true, or a different value, and then this would be false. Refutable. A formula is refutable if there are an assignment S and a structure M that refute it, that is, the assignment S does not satisfy the formula in M. It is as if someone says, quote, every day in August is rainy, unquote, and you refute it by pointing out that in the year 1996 there was a day in August when it did not rain. Here are some examples from predicate logic. Exists x p0x implies for all x p0x. Now, this may be true in some models under some assignment, but this can be refuted by making the hypothesis that exists x p0x true and the conclusion for all x p0x false. Next example. For all x there exists y r0xy implies exist y for all x r0xy. Again, this can be made true very easily, but that's not relevant. We can refute this by making the hypothesis true and the conclusion false. Hypothesis can be made true by choosing the relation R0 suitably so that for every x there is a y, so that the pair xy is in the relation, but at the same time making sure that it's not true that there is one y which works for every x. Finally, x equals y, this is refutable. because we can think of an assignment in a model with at least two elements so that the assignment assigns different values to x and y. Contradiction. In everyday language, a person utters a contradiction if he or she says something which is false merely because of its form, like, quote, I am a vegetarian and I am not a vegetarian. Contradicting oneself in a social situation is problematic and usually leads to being ignored or else asked to clarify what one means. If one utters only validities in a conversation, one does not make much progress. It is the same with contradictions. Therefore, people usually utter contingencies, statements that could be right or wrong. In everyday life, as also in science, contingencies are judged in the light of empirical data. If I say, quote, it rained yesterday in New York, unquote, I could be a priori right or wrong. So it is a contingency. But of course we can check the meteorological data and make an a posteriori judgment that my statement was right or wrong. A formula of predicate logic is a contradiction if it is not satisfied by any assignment in any structure. Here are some examples from predicate logic. For all x a and exist x not a. So this is a contradiction because it cannot be the case that every x is in A and some x is not in A. Next formula, exist x A and for all x not A. This is similar to the previous. Then for all x, left parenthesis A implies B, right parenthesis, and exists x, left parenthesis A and not B, right parenthesis. This is a contradiction because the first conjunct says that everything in A is in B, and the second conjunct says something is in A but not in B, so these clearly contradict each other. Finally, an example from identity. X equals Y and X equals Z and not Y equals Z. So this is a violation of the transitivity axiom of identity. Because the formula has identity, we assume that every model that we consider satisfies the identity axioms, and this clearly violates the transitivity axiom. Categories of formulas of predicate logic. Every formula of predicate logic is either a validity, a contradiction, or a contingency. Every satisfiable formula is either valid or contingent, and every refutable formula is either a contradiction or a contingency. So we have these three disjoint categories: contradictions, contingencies, and validities. And the union of contradictions and contingencies are called refutable, and the union of contingencies and validities is called satisfiable. Recognizing what the type of a given formula is, whether it is a validity, a contradiction, or a contingency, is the bread and butter of a logician. However, this may be a difficult task. Hard question. Given a formula, can we decide mechanically whether it is a validity, a contradiction, or a contingency? This is a hard question because it can be proved mathematically that this is not possible if mechanically is interpreted as is now common. The usual current definition of being decidable mechanically, which is due to the British mathematician Alan Turing, is roughly the same as being decidable in finite time by a computer program which has a finite but endless amount of time and memory. The method of deductions. Given a potential deduction for a formula A, it is not difficult to check whether the deduction is correct or not. And this can be done completely mechanically. Indeed, such computer programs exist and they are called proof checkers. One can simply make a list of all possible deductions and check them one by one. The hard case is when there is no deduction, so it takes infinite time to find it out. So, suppose I want to use a method of deductions to decide what is the type of a formula A. Is it a validity, a contradiction, or a contingency? So first I try to prove it. I start going through deductions. I can do that mechanically, simply trying every possible deduction. Now if I hit a deduction of A, then A is valid. But what if I don't hit? I have to wait forever, because there are infinitely many different kinds of deductions. So I will never know the answer. Maybe my formula is not at all valid. Maybe it is refutable. Well, maybe it is a contradiction. So I can simultaneously start trying to prove not A. I go through all possible deductions and try to prove A, and at the same time I go through all possible deductions in order to prove not A. But what if A is a contingency? Then neither of these infinite processes ever ends. That is the real problem. To demonstrate contingency, I would have to construct a model for A and a model for negation of A. But these models are infinite. They cannot be created mechanically. They can only be constructed by using mathematics. Equivalence of formulas. Two formulas of predicate logic, A and B, are called logically equivalent or simply equivalent if A, if and only if B, is a validity. Equivalence of formulas is used in everyday language and in science all the time, often without paying much attention to it. And it is part of learning logic to distinguish simple logical equivalences. They are the basics of logic. So let us look at some simple equivalences. The formula for all x, A, is equivalent to negation exists x, negation A. The formula exists x A is equivalent to negation for all x, negation A. The formula for all x, left parenthesis A and B, right parenthesis, is logically equivalent to for all x A and for all x B. Exists x, left parenthesis A or B, right parenthesis, is logically equivalent. Exists x A or exists x B. Exist x, exist y A is logically equivalent to exist y, exists x A. For all x, for all y A is logically equivalent to for all y, for all x A. For all x, left parenthesis A implies B, right parenthesis, is logically equivalent to exists x A implies B when x is not free in B. This is a less obvious logical equivalence than the previous ones. We start with something with a universal quantifier and we end up with something with an existential quantifier, but note that the existential quantifier is in the hypothesis of an implication, while in the universal formula the universal quantifier is in front of the whole formula. The next example, for all x, left parenthesis A implies B, right parenthesis, is logically equivalent to A implies for all x B, when x is not free in A. So x doesn't matter to A, so we can take it out of the range of the universal quantifier. The same for existential quantifier is the last example. Exists x, left parenthesis A and B, right parenthesis, is logically equivalent to exist x, A and B. Again, we assume that x is not free in B, so whatever x is doesn't matter to B, and B can be taken out of the range of the quantifier. Suppose we have to decide whether A is satisfiable or a contradiction. One method that is possible is to build a semantic tree for A. If all branches end up closed, then we have a semantic proof of negation A. Strictly speaking, a semantic proof of negation A is a semantic tree for negation A, but the two negations can easily be eliminated in the semantic tree. And then we can conclude that A is a contradiction. On the other hand, if we apply all the rules to their fullest extent and still have a branch which is not closed, then we can use this branch to build a model for A, and then A is satisfiable. Note that in this case the branch may also be infinite. So the semantic tree method can be used both to construct a model and to construct a proof. It all depends on whether the branches close or not. But it is important that one uses the rules to their fullest extent. Of course, once all branches are closed, there's no need to use any rules anymore, because closed branches will not open when new rules are used. What is closed, will always be closed. But if you have open branches which are not closed, then you have to look whether you have not used some rule yet. And when you do this, you may end up with an infinite branch. But still it can be used to construct a model for A.